The information provided in this video is for educational and entertainment purposes only and does not constitute professional career, financial, or mechanical advice. Automotive repair involves inherent risks, including physical injury and property damage. The techniques, tools, and procedures discussed are based on specific case studies and historical industry trends, which may not apply to every vehicle or situation. Viewers are strongly encouraged to consult with certified professionals, adhere to manufacturer service manuals, and conduct their own due diligence before attempting any repairs or making career-level investments in the automotive industry. No specific earnings or employment outcomes are promised or assured. The average American driver spends nearly $1,000 a year on unexpected vehicle maintenance, yet over 70% of those drivers feel they are being overcharged every time they hand over their keys. While most people see a repair shop as a place where money goes to disappear, the person on the other side of that heavy steel bay door is fighting a battle that the public rarely sees. Imagine waking up at 5 a.m., knowing that by noon, you will be responsible for the structural integrity of a 3-ton machine moving at 70 miles per hour. One loose bolt, one overlooked sensor reading, or one miscalculation in a hydraulic line could be the difference between a satisfied customer and a catastrophic mechanical failure. But here is the shocking statistic that most people outside the industry do not realize. Despite the massive demand for skilled labor, the United States is currently facing a shortage of over 600,000 automotive technicians. We are living in an era where the cars are getting smarter, but the hands capable of fixing them are becoming a rare commodity. Today, we are pulling back the grease-stained curtain to show you the high-stakes reality of a master technician. You will see why that check engine light is often the least of our worries, and how the modern shop has evolved from a simple garage into a high-tech laboratory where computer science meets heavy metal. This video is designed to solve the two biggest problems facing the American automotive landscape today: the lack of transparency for the consumer and the lack of a realistic roadmap for those considering this career path. If you are a vehicle owner, this deep dive will arm you with the specific knowledge to understand exactly what is happening under your hood, potentially saving you thousands in unnecessary repairs by teaching you how to communicate with your mechanic. If you are someone looking at the trades as a viable future, we are going to break down the technical skill sets, the specialized tool investments, and the diagnostic frameworks required to thrive in a digital-first automotive world. We are moving beyond the surface-level oil change vlogs. This is a masterclass in the mechanical soul of the United States. To understand the day of a technician, you first have to understand the psychological weight of the morning arrival. It is 7:30 a.m. in a suburb of Chicago, and the air is thick with the smell of recycled oil and industrial-grade floor cleaner. As the bay doors roll up, the technician is not just greeted by a list of tasks, they are greeted by a rack of work orders that represent the anxiety of the local community. There is the single mother whose minivan has a mystery stall, the contractor whose entire livelihood depends on a diesel engine that refuses to prime, and the enthusiast whose vintage muscle car is leaking fluid from an unidentified seal. This is where the first technical hurdle begins, the triage phase. In a high-volume shop, the ability to prioritize work is just as important as the ability to turn a wrench. Let's look at a historical trend in the industry. 20 years ago, a technician's primary tools were mechanical, sockets, wrenches, and pry bars. Today, the most important tool in the shop is often a ruggedized laptop, equipped with an OBD2 interface and proprietary manufacturer software. Before a single bolt is turned on that stalling minivan, the technician must perform a full system scan. This isn't just about reading a code, it's about interpreting data streams. When a scan tool shows a P0300 random misfire code, a novice might start throwing spark plugs at the problem. A master technician, however, looks at the freeze frame data. They analyze the fuel trim levels, the oxygen sensor voltages, and the crankshaft position sensor synchronization at the exact millisecond the fault occurred. This is the difference between a parts changer and a diagnostic technician. One costs the customer hundreds in unnecessary parts. The other finds the frayed wire hidden behind the intake manifold that was grounding out against the firewall. Step by step, the morning begins with a multi-point inspection or MPI. This is a rigorous 30 to 40 point check that covers everything from tire tread depth, measured in 32 NDS of an inch, to the clarity and pH balance of the engine coolant. For example, consider the braking system. A technician doesn't just look to see if the pads are thin. They examine the rotor surface for heat checking or bluing, which indicates a sticking caliper. They check the brake lines for swelling or corrosion, especially in the Salt Belt states where road brine eats through steel like acid. They check the moisture content of the brake fluid using a refractometer, because brake fluid is hygroscopic, meaning it absorbs water from the air, which can lead to internal boiling and brake failure under heavy loads. This level of detail is what ensures a vehicle is truly roadworthy, rather than just running. As the clock hits 10 a.m., the physical toll of the job starts to manifest. The automotive technician is an industrial athlete. You are constantly in unfavorable ergonomic positions, reaching over fenders, crouching under lifts, and using high-torque impact guns that vibrate through your joints. Case studies of long-term industry professionals often show a high prevalence of repetitive strain injuries, which is why modern technicians invest heavily in ergonomic tool carts and lift systems. But the mental strain is even higher. Consider the complexity of a modern transmission. A 10-speed automatic transmission is a marvel of planetary gear sets, hydraulic valves, and electronic solenoids. When a customer complains of a harsh shift, the technician has to determine if it is a mechanical failure within the clutch packs, a hydraulic pressure issue in the valve body, or a software glitch in the transmission control module. This requires a deep understanding of fluid dynamics and binary logic. In this deep dive, we are also addressing the financial reality of the flat rate system, which is the standard compensation model in most U.S. dealerships and large independent shops. Under this system, a technician is paid based on the book time of a job, not the actual hours spent. If a water pump replacement is rated for 4 hours and the technician finishes it in 2, they are paid for 4. However, if the bolts are rusted and the job takes 6 hours, they are still only paid for 4. This creates a high-pressure environment where efficiency is king, but accuracy is mandatory. It requires a massive personal investment in tools, often ranging from $25,000 to over $100,000 throughout a career, stored in massive tool chests that act as a technician's mobile office. By the end of this 10-part series, you will understand the nuances of electrical diagnostics, the chemistry of modern synthetic lubricants, the physics of suspension geometry, and the business logic that keeps a shop profitable in a fluctuating economy. We are starting with the foundation, the morning rush, and the diagnostic mindset, because before you can fix the machine, you have to understand the language it speaks. Stay with us as we move into the heavy line, repairs where the engines come out and the real surgery begins. Imagine a scenario in 2026 where a client named Marcus pulls his electric hybrid pickup truck into the service bay. To the untrained eye, the truck looks perfect, but Marcus reports a subtle shudder during regenerative braking. In the world of heavy line repairs, this is where the physical labor meets high-voltage complexity. The transition from the diagnostic bay to the heavy lift is a shift in both mindset and equipment. We are no longer just looking at data streams, we are preparing to separate the heart of the vehicle from its chassis. Heavy line work traditionally referred to internal engine repair, transmission overhauls, and differential rebuilds. In the current automotive landscape, this definition has expanded to include the removal and servicing of massive battery arrays and integrated drive units. The first step in any heavy line operation is the environmental setup. A technician does not just start unbolting components. They must establish a sterile field. In a modern U.S. shop, this involves deploying specialized heavy-duty lifts capable of handling 10,000 pounds or more, ensuring the center of gravity is perfectly calculated. For Marcus's truck, the technician must first perform a high-voltage disable procedure. This is a critical safety step involving insulated tools rated for 1,000 volts and Category 3 electrical gloves that are air-tested for leaks before every single use. Historical trends in shop safety show that the move toward electrification has mandated a level of discipline formerly reserved for aerospace engineers. One mistake in the lockout-tagout procedure could lead to a thermal event or a lethal discharge. Once the vehicle is de-energized, the mechanical surgery begins. Let's look at a case study involving a classic internal combustion engine failure, a 2021 heavy-duty work van with a cracked cylinder head. The technician, let's call him Jackson, has to perform what is known as a cab-off repair. In many modern American trucks and vans, the engine is tucked so far under the cowl that the most efficient way to access it is to literally disconnect the entire body of the vehicle from the frame and lift it into the air. Imagine the precision required to disconnect steering linkages, brake lines, electrical harnesses, and cooling ducts, then lifting the entire passenger compartment 6 feet into the air, leaving the engine and drivetrain exposed on the rails. This is not just mechanics. This is large-scale industrial engineering performed in a local shop. Jackson now faces the engine block. In a deep dive masterclass, we must discuss the reality of torque-to-yield fasteners. Many people believe you can just tighten a bolt until it feels snug. In heavy line work, that approach leads to catastrophic failure. Modern engines use bolts designed to stretch at a molecular level when tightened. Jackson must use an electronic torque wrench that measures both foot-pounds and degrees of angle. For a cylinder head, the specification might be 30 foot-pounds plus an additional 90-degree turn. This ensures the head gasket is crushed with exactly the right amount of force to contain thousands of pounds of combustion pressure. If Jackson is off by even 5 degrees, the potential outcome is a blown gasket 3 months down the line, a mistake that would cost the shop thousands in warranty labor. As we move deeper into the engine, we encounter the complexity of variable valve timing or VVT systems. These systems use oil pressure to rotate the camshafts independently of the crankshaft, allowing the engine to breathe better at high speeds while maintaining efficiency at idle. When these systems fail, it is often due to poor maintenance. Imagine if the oil passages, which are sometimes no wider than a needle, become clogged with carbon deposits. The technician must use precision micrometers and feeler gauges to check for where that is invisible to the naked eye. We are talking about tolerances of 0.001 inches. To put that in perspective, a human hair is roughly 0.003 inches thick. The technician is working with margins 3 times smaller than a strand of hair. While Jackson is dealing with the engine, another technician across the shop is tackling a transmission rebuild. This is perhaps the most daunting task in the heavy line category. A modern 10-speed automatic transmission contains hundreds of individual parts, including friction plates, steel discs, one-way clutches, and a complex hydraulic brain known as the valve body. The technician must disassemble this unit on a dedicated clean bench. Even a single speck of lint from a shop rag can clog a solenoid and cause the transmission to fail its initial calibration. This is why you see technicians using specialized lint-free wipes and surgical-grade cleaning solvents. The business side of this labor is equally intense. In the United States, heavy line technicians are often the highest-paid individuals in the shop, but they also carry the most risk. Under the flat rate system mentioned previously, a transmission overhaul might pay 12 hours of labor. If the technician can complete it in 9 hours due to superior skill and expensive specialized tools, they have increased their effective hourly rate. However, if they encounter a seized bolt or a backordered part, that vehicle occupies their lift for days, preventing them from taking on new work. This is the opportunity cost that defines the financial life of a professional mechanic. It requires a delicate balance of speed, precision, and inventory management. In 2026, we also see the integration of augmented reality in these heavy repairs. Some technicians are now using AR headsets that overlay the torque sequences and wiring diagrams directly onto their field of vision. Imagine Jackson looking at the engine block and seeing a digital ghost of the bolts, numbered in the exact order they must be tightened. This technology reduces the cognitive load and helps prevent the forgotten bolt syndrome that can plague even the most experienced veterans. Yet, despite the tech, the job still requires the feel of the metal. The ability to know when a thread is about to strip or when a bearing has just a bit too much play. Let's discuss the chemistry of the fluids involved. A heavy line technician isn't just a plumber. They are a fluid analyst. When draining a differential or a transfer case, the technician looks for glitter, tiny metallic flakes that tell a story of internal wear. They use magnetic drain plugs to capture these particles. The color, smell, and viscosity of the fluid provide a roadmap of the vehicle's history. Dark, burnt-smelling fluid suggests overheating and heavy towing, while milky fluid indicates a breach in the cooling system, leading to water contamination. Identifying these signs early can save a customer from a $5,000 replacement by catching a $200 seal failure. As the sun passes its peak and the afternoon heat settles into the shop, the heavy line technician is often at their most exhausted. They have been wrestling with iron and steel for 6 hours. Their hands are covered in a mixture of assembly lube and degreaser. But this is where the most critical phase begins, the reassembly. It is a common saying in the industry that anybody can take it apart, but it takes a mechanic to put it back together. Every harness must be routed in its factory location to avoid heat damage. Every clip must be snapped in tight to prevent rattles that will frustrate the customer. The complexity of these machines is only increasing. We have moved from simple mechanical linkages to drive-by-wire systems where there is no physical connection between your foot and the engine's throttle, or your hand and the transmission's gears. Everything is an electrical signal sent over a controller area network or CAN bus. This leads us to a massive question. What happens when the mechanical repair is finished, but the computer refuses to acknowledge it? The heavy line work is only half the battle. Once the engine is back in and the fluids are topped off, the vehicle enters the digital relearn phase. This is where the technician must bridge the gap between hardware and software. If you think the physical labor was intense, wait until you see the high-stakes world of module programming and ADAS calibration. In the next part, we will explore why a simple windshield replacement now requires a laser-guided computer alignment, and what happens when the car's brain starts arguing with its new parts. The moment the mechanical repairs are finished, the technician enters the realm of the invisible. In 2026, a vehicle is no longer just a collection of gears and pistons. It is a rolling local area network with up to 100 separate electronic control units or ECUs. Imagine a customer named Sarah who just had her front bumper and windshield replaced after a minor collision. In the year 1996, she would have driven away as soon as the paint was dry. In 2026, her car is essentially blind and dangerous until a technician performs a comprehensive ADAS calibration. ADAS stands for Advanced Driver Assistance Systems, and it governs everything from adaptive cruise control to automatic emergency braking and lane keep assist. The calibration process begins with a clean bay and a perfectly level floor. Even a slope of 1% can throw off a radar sensor's pitch, causing the car to see an overhead bridge as a stalled vehicle on the road. The technician, let's call him David, sets up a series of physical targets at precise distances from the front bumper using laser measuring tools. This is a meticulous step-by-step procedure. First, David must ensure the fuel tank is full, and the tire pressures are exactly to the manufacturer's placard. Why? Because the weight of the fuel and the height of the tires change the ride height of the vehicle, which in turn changes the angle of the forward-facing camera mounted behind the rearview mirror. David connects a high-end diagnostic tablet to the vehicle's gateway module. This is the air traffic controller of the car's data. He initiates a dynamic calibration for the camera and a static calibration for the radar. During a static calibration, the car remains stationary while the computer learns the position of the physical targets David placed in the shop. This is a game of millimeters. If the radar sensor is off by just 1 degree at the bumper, that error expands to several feet by the time the radar beam travels 200 feet down the highway. Historically, miscalibrated sensors have led to phantom braking events, where a car slams on its brakes for no apparent reason, creating a massive safety risk for the driver and those behind them. Once the static calibration is greenlit, David must take the car for a dynamic calibration. This involves driving the vehicle at a steady speed on a road with clear lane markings and a specific amount of ambient light. The car's onboard processors are essentially learning how to see the world again. Sarah's car is processing millions of data points per second, comparing the camera's visual feed with the radar's distance data and the wheel speed sensor's input. If these 3 data streams do not align, the system will throw a fault code and disable all safety features. This is the brain of the car arguing with its new physical reality. But the complexity does not stop at safety sensors. We must look at the high-stakes world of module programming and coding. When David replaces a component as seemingly simple as a power window motor or a battery on a high-end European or American luxury vehicle, he cannot just plug it in and walk away. The vehicle's central gateway must be told that a new part has been installed. This is known as registration or initialization. For example, a modern intelligent battery sensor monitors the age and health of the battery to adjust the alternator's charging output. If David installs a new battery but does not register it with the computer, the alternator will continue to charge the new battery as if it were an old, failing one, potentially shortening its lifespan by 50% within the first year. Case studies in 2026 show an increasing trend of component protection. This is a security feature implemented by manufacturers to prevent the use of stolen parts. If David installs a used infotainment module from a salvage yard into Sarah's car, the vehicle may recognize that the serial number or VIN encoded in that module does not match the rest of the car's network. The car will then enter a limp mode or disable the audio system entirely. To resolve this, David must use a secure, manufacturer-sanctioned internet connection to Handshake with a server in Detroit or Munich to authorize the part. This transition from mechanical labor to digital security specialist is why the modern technician's toolkit now includes high-speed Wi-Fi extenders and Ethernet to OBD cables. Now, imagine the frustration when the computer refuses the handshake. This is where the technician's role as a forensic data analyst comes into play. David might spend 2 hours chasing a U code, which is a communication fault. These are the most dreaded codes in the industry. It means two or more computers are not talking to each other. The cause could be a pin-sized hole in a wire, a corroded ground strap, or network noise caused by a failing aftermarket LED headlight bulb that is leaking electromagnetic interference into the CAN bus. David uses an oscilloscope, a tool that graphs electrical voltage over time, to look at the actual square waves of the data packets. If the waves are jagged or flatlined, he knows exactly which part of the conversation is being interrupted. This digital deep dive also involves flash programming. Just like your smartphone gets software updates to fix bugs or improve performance, cars receive calibration updates. A manufacturer might release a software patch to improve shift quality in a transmission, or to prevent a specific sensor from being too sensitive in the rain. David must connect the car to a steady 100 amp hour supply during this process. If the car's voltage drops even slightly while the computer's flash memory is being rewritten, the module can become bricked, meaning it is permanently rendered useless, essentially becoming a very expensive paperweight. The tension in the shop during a 20-minute flash sequence is palpable. It is a high-wire act where the potential outcome of a mistake is a $3,000 replacement bill. To add another layer of value to this masterclass, we must discuss the digital twin technology emerging in 2026. Some high-end diagnostic suites now create a virtual model of the specific vehicle on the technician's screen, highlighting exactly where the electrical resistance is too high based on real-time sensor data. This allows David to see through the dashboard and pinpoint a loose connector without tearing the entire interior apart. However, even with this tech, the technician still needs the fundamental knowledge of Ohm's law and Kirchhoff's circuit laws to verify that the computer's guess is actually correct. As the afternoon progresses, David finishes the calibrations on Sarah's car and moves to the next challenge, a vehicle that passed all its computer tests but still feels wrong to the driver. This brings us to the intersection of human intuition and mechanical reality. The computer can tell you if a circuit is open, but it cannot always tell you if a suspension bushing is slightly too soft, or if a tire has a flat spot that only vibrates at 62 miles per hour. The technician must now pivot from being a quarterback to being a mechanical detective. The day is far from over. While the digital world is complex, the physical world of NVH, noise, vibration, and harshness, is where many technicians lose their minds. A squeak in a dashboard can be more difficult to find than a short circuit in a wiring harness. In the next part, we are going to dive into the specialized world of NVH diagnostics. You will learn how we use chassis ears, microphones clipped to the underside of the car, to listen to the internal groans of a wheel bearing, and why a simple pebble stuck in a brake shield can sound like a catastrophic engine failure. The mystery of the unidentifiable noise is about to be solved. The hunt for a noise that shouldn't exist is perhaps the most mentally taxing part of a technician's afternoon. Imagine a customer named Robert who brings in his 2024 luxury SUV. Robert is meticulous. He notices a faint rhythmic clicking only when he is turning left at speeds between 15 and 22 miles per hour, but only after the car has been driven for at least 30 minutes. To a service advisor, this sounds like a needle in a haystack. To a technician like Elena, this is the start of a deep dive investigation into noise, vibration, and harshness, or NVH. In the United States, NVH has become a primary driver of customer dissatisfaction, because modern vehicles are so quiet that even the smallest rattle sounds like a drum set in the back seat. Elena begins by performing a test drive with Robert to verify the concern. This is a critical step. If the technician cannot replicate the noise, they cannot fix it. She uses a specialized tool called a chassis ear system. This is a kit containing several wireless microphones with heavy-duty clamps. Elena attaches these microphones to specific strategic locations. One on the left front lower control arm, one near the outer constant velocity or CV joint, one on the steering rack housing, and one on the wheel bearing carrier. As she drives, Elena wears a set of studio-quality headphones connected to a receiver that allows her to switch between the microphones in real time. This is the mechanical equivalent of a doctor using a stethoscope to listen to individual heart valves. While turning left, she toggles to the CV joint microphone. The sound is clean. She toggles to the wheel bearing. There it is, a low-frequency growl that is just beginning to develop. A wheel bearing failure is often deceptive. Historically, a bad bearing would howl like a jet engine at highway speeds. However, with the precision-engineered hubs of 2026, a bearing can have a microscopic flat spot on one of its internal steel balls that only creates a resonance under specific lateral loads. By using the chassis ear, Elena avoids the parts cannon approach. She doesn't just guess and replace the entire front axle. She identifies that the bearing is the culprit, saving Robert from a potential outcome of paying for 3 different repairs before the right one is found. This diagnostic accuracy is what separates a master technician from an entry-level oil changer. But NVH isn't always about failing parts. Sometimes it is about physics and frequency. Consider a case study involving a recurring vibration in a fleet of delivery vans. The drivers reported a shimmy in the steering wheel at exactly 65 miles per hour. The tires were balanced, the alignment was perfect, yet the vibration remained. The technician discovered that the vibration was actually an engine order harmonic. A failing dual-mass flywheel was vibrating at a frequency that matched the resonant frequency of the steering column at a specific RPM. Imagine the level of engineering knowledge required to understand that a vibration felt in your hands is actually being generated by a component 6 feet away inside the transmission bell housing. Step by step, solving an NVH issue requires a process of elimination. First, Elena checks for the obvious. Loose lug nuts, stones trapped in the brake dust shields, or plastic undertrays that have lost their clips and are flapping in the wind. A common scenario involves a customer complaining of a scraping metal sound. Often, it is simply a thin metal shield behind the brake rotor that has been slightly bent, making contact with the rotor as it expands from heat. A 30-second adjustment with a pry bar solves a problem that the customer feared was a $2,000 brake overhaul. In 2026, we also deal with active noise cancellation, or ANC. Many American cars use the interior speakers to play anti-noise frequencies that cancel out engine drone. If a technician installs an aftermarket exhaust or if a door speaker fails, the ANC system can actually create a weird, booming pressure sensation in the cabin that makes the driver feel nauseous. Elena has to use a specialized signal generator to test the interior acoustics and ensure the car's computer isn't accidentally fighting itself. This highlights the intersection of audio engineering and automotive repair. Beyond the ears, a technician uses their sense of touch. A vibration is just a noise you can feel. Elena uses an electronic vibration analyzer, or EVA. This handheld device uses an accelerometer to measure the frequency of a vibration in hertz. By entering the tire size and the vehicle speed into the tool, the EVA can tell her if the vibration is coming from a component rotating at tire speed, such as a flat spot on a tire or a bent rim, or if it is at drive shaft speed, which would indicate a failing U-joint or an imbalanced prop shaft. For instance, a vibration at 15 Hz usually points to a tire issue, while a vibration at 80 Hz is almost always driveline related. This level of detail is necessary because the United States infrastructure, specifically the varying quality of asphalt and concrete, creates a massive range of road-induced noise. A technician must be able to distinguish between tire growl, caused by specific tread patterns on concrete highways, and an actual mechanical failure. Case studies show that many repairs are actually just the result of a customer switching to a lower quality tire brand with a harder rubber compound that transmits more road noise into the cabin. But what happens when the noise is coming from inside the engine? This is where the diagnostic stakes reach their peak. Elena uses a traditional mechanical stethoscope to probe the engine block. She is listening for piston slap, rod knock, or valve train tick. Each has a distinct signature. A rod knock is a deep, heavy thud that gets louder under load, indicating that the bearing between the connecting rod and the crankshaft has failed. This is a terminal diagnosis for an engine. Conversely, a valve tick is a lighter, faster sound that occurs at half the speed of the crankshaft. Understanding these rhythmic patterns is like a musician identifying a syncopated beat. Imagine if Elena misdiagnoses a simple exhaust leak as an internal engine knock. She might tell the customer they need a $10,000 engine replacement, when all they really need is a $50 gasket. This is why the technician's integrity is the most valuable tool in the shop. In a world of complex sensors, the human ear and the ability to interpret mechanical rhythm remain irreplaceable. As we look at the clock, it is now 3:30 p.m. The afternoon slump is a myth in a busy shop. This is when the waiters, customers who chose to stay in the lounge, start getting restless. The pressure to finish the NVH diagnostics and move into the final safety checks of the day is immense. But there is a hidden side to the shop that most people never see: the management of hazardous waste and the constant battle against environmental contamination. The fluids we drained earlier, the tires we replaced, and the lead-acid batteries we pulled, none of it can just be thrown away. In the next part, we are going to look at the green side of the automotive industry. You will see how a modern shop handles thousands of gallons of toxic chemicals, and why the eco-friendly label on your repair bill is more than just marketing. We are going to explore the massive recycling infrastructure that keeps the American automotive industry from becoming an environmental disaster, and how the shift to lithium-ion batteries is changing the end-of-life protocols for every vehicle on the road. The day is far from over, and the most physically demanding tasks are often saved for the final stretch. Stay tuned as we dive into the world of industrial waste management and the high-voltage recycling challenges of the near future. The transition from mechanical diagnosis to industrial waste management is where the automotive technician transforms into a steward of the environment. In the United States, the automotive service industry generates millions of tons of hazardous waste annually, and by 2026, the complexity of this waste has reached a peak due to the coexistence of internal combustion engines and massive lithium-ion battery packs. Imagine a technician named Carlos who has just finished a busy afternoon. He looks at the various collection basins scattered across his bay. There is used motor oil, ethylene glycol coolant, brake fluid, and a pile of lead-acid batteries. Each of these substances requires a specific, federally mandated disposal protocol to prevent soil and groundwater contamination. The backbone of this system is the Resource Conservation and Recovery Act, or RCRA. Under these regulations, a shop is not just a repair facility. It is a generator of hazardous waste. Step by step, Carlos must verify that every fluid is segregated. If he accidentally mixes a small amount of chlorinated brake cleaner into a 500-gallon tank of used motor oil, the entire tank becomes hot waste. Historically, the cost to dispose of contaminated oil is 10 times higher than clean used oil because it can no longer be easily refined into marine fuel or heating oil. This is a critical financial and environmental point. The technician's discipline at the drain bucket directly impacts the shop's bottom line and the local ecosystem. Consider the case study of used engine coolant. Modern coolants are no longer just green water. They are sophisticated chemical cocktails containing organic acid technology and phosphates designed to protect aluminum engine blocks from cavitation. When Carlos drains this fluid, it cannot go down the sink. He pumps it into a dedicated recycling unit right on the shop floor. This machine uses vacuum distillation and a series of filters to remove heavy metals like lead and copper that the fluid picked up inside the engine. The potential outcome of this process is a recycled fluid that meets original equipment manufacturer specifications, reducing the need for virgin chemical production. As we look deeper into the year 2026, the most significant challenge in the waste stream is the end-of-life management of electric vehicle batteries. Imagine if a technician is tasked with decommissioning a battery pack from a vehicle that was involved in a flood. This is a high-stakes scenario. The pack might still hold a charge of 400 to 800 volts, but the internal cells could be compromised. Carlos must use specialized fire suppression containers filled with expanded glass beads to store these modules. This technology is designed to absorb the heat and toxic gases if a thermal runaway occurs. In the United States, the recycling infrastructure for these batteries is currently scaling up, with facilities using hydrometallurgical processes to recover 95% of the lithium, cobalt, and nickel. The technician is the first link in this multi-billion-dollar circular economy. The physical labor of waste management is also grueling. A standard lead-acid battery weighs roughly 40 pounds. A busy shop might swap out 15 batteries in a single day. That is 600 pounds of lead and sulfuric acid that must be palletized, shrink-wrapped, and documented for pickup. In the USA, lead-acid batteries are the most recycled consumer product, with a recovery rate of nearly 99%. This is a success story of industrial cooperation, where the core charge system incentivizes every player in the chain, from the driver to the technician, to return the old unit. But what about the parts that aren't fluid or metal? Let's talk about tires. Every year, the United States generates over 250 million scrap tires. When Carlos pulls a set of bald tires off a customer's car, they don't just go to a landfill. They are stacked in a tire corral for specialized haulers. These tires are often shredded to become tire-derived fuel for cement kilns or crumb rubber for playground surfaces and asphalt additives. In 2026, some manufacturers are even experimenting with pyrolysis, which breaks the tire down into its original oil and carbon black components. The technician's role is to ensure these tires are stored in a way that prevents them from becoming breeding grounds for mosquitoes or fire hazards. Step by step, the technician also manages the shop rags and oil absorbents. These are not just thrown in the trash. The rags are placed in fireproof oily waste cans and sent to an industrial laundry service that captures the oil before washing the fabric. The floor dry, that clay-like gravel used to soak up spills, must be swept up and placed in designated drums. This meticulous attention to detail is why modern American shops no longer have the grimy garage feel of the 1970s. They are increasingly resembling clean room environments where chemical safety is a top priority. Imagine the scenario of a spill response. If a hydraulic line on a lift bursts, sending 5 gallons of fluid across the floor, the shop enters a lockdown mode. Carlos and his team deploy socks, long absorbent tubes, to surround the drains. They use pads to lift the bulk of the fluid. Every used pad and sock is weighed and logged in the shop's environmental compliance binder. This is not just red tape. It is a legal requirement enforced by the Environmental Protection Agency. Fines for improper hazardous waste management can reach tens of thousands of dollars per day, making the technician's knowledge of safety data sheets as important as their knowledge of a torque wrench. Let's look at the data regarding evaporative emissions. Even the air in the shop is managed. Modern fuel systems are closed-loop, meaning gasoline vapors are captured in charcoal canisters. When a technician like Carlos is working on a fuel pump, they use vapor recovery systems to ensure that volatile organic compounds are not released into the atmosphere. This protects the health of the workers and the air quality of the surrounding community. Historical trends show that shop-related respiratory issues have plummeted since the implementation of these high-efficiency ventilation and recovery systems. This green side of the masterclass highlights a fundamental shift in the career of an auto repair technician. You are no longer just fixing cars. You are a specialized technician operating within a strict regulatory framework that balances consumer mobility with environmental protection. The complexity of managing these materials, from the high-voltage risks of lithium-ion to the chemical nuances of organic acid coolants, requires constant ongoing education. As the clock strikes 4:15 p.m., the bay floors are scrubbed, the waste containers are sealed, and the documentation is finalized. But the day is not quite over. We have dealt with the mechanical, the digital, the auditory, and the environmental. Now we must face the most unpredictable element in the entire shop: the customer communication and the service write-up. In the next part, we are going to pull back the curtain on the front-of-house operations. You will see how a technician's technical findings are translated into a digital inspection report that lands on a customer's smartphone. We will explore the psychology of the service advisor, the art of explaining complex repairs to a non-technical audience, and why the most difficult part of the job isn't fixing the car, it's managing the expectations of the person who drives it. The bridge between the grease-stained bay and the glass-walled waiting room is where the real business of automotive repair happens. The transition from the mechanical bay to the front office is often the most jarring part of a technician's afternoon. Imagine a technician named Leo who has just spent 3 hours diagnosing a complex intermittent electrical short in a 2024 hybrid SUV. His hands are calloused, his uniform has the faint scent of dielectric grease, and his brain is saturated with wiring diagrams. Now he must pivot. He is no longer an engineer. He is a communicator. In the United States automotive industry of 2026, the tool that carries as much weight as a scan tool is the Digital Inspection Report, or DIR. Leo grabs a ruggedized tablet and begins the process of documentation. This is not just a list of parts. It is a narrative constructed for a non-technical audience. He starts with the high-definition photography module. Step by step, he documents the state of the vehicle. He takes a clear, well-lit photo of the frayed wiring harness he found tucked behind the inverter assembly. He then uses a digital stylus to circle the copper exposure in bright red. This visual evidence is a cornerstone of modern consumer trust. Historical trends in the US show that when a customer can see the physical defect on their own smartphone screen while sitting in the waiting room or at their office, the authorization rate for necessary repairs increases by over 40%. Consider a case study involving a customer named Mia. Mia brought her car in for a simple oil change, but Leo discovered that her rack and pinion bellows were torn, leaking power steering fluid onto the hot exhaust manifold, a potential fire hazard. In the past, a service advisor would have called Mia and tried to explain what a bellows boot is over the phone. Mia, feeling overwhelmed and skeptical, might have declined the repair, thinking it was an upsell. In 2026, Leo records a 15-second video. He points his flashlight at the leak, wipes a gloved finger across the fluid to show its color, and explains in plain English why this matters for her safety. This video is sent via text message. Mia watches it, understands the mechanical reality, and clicks approve within minutes. This is the transparency revolution in the American auto shop. The translation of technical data into financial estimates is where the service advisor, a person named Sean in this scenario, comes into play. Sean acts as the filter between Leo's technical world and Mia's budgetary world. Sean has to take Leo's notes, which might say replace rack and pinion, perform four-wheel alignment, flush system, and turn them into a comprehensive quote. This involves looking up labor times in a database like AllData or Mitchell 1. In the US, these labor times are standardized based on decades of historical data. If the book says a steering rack takes 4.8 hours, that is what the customer is billed, regardless of whether Leo finishes in 3 or 6. Imagine the high-pressure conversation when Sean has to explain a hidden repair. Sometimes, once a technician begins a job, they find secondary damage that was impossible to see during the initial inspection. For example, while removing the steering rack, Leo might find that the subframe bolts are so badly corroded from Midwestern road salt that they have seized and require induction heating or drilling to remove. Sean now has to call the customer and explain why the initial $1,500 estimate has just climbed by another $300. This is where the customer experience is won or lost. Sean doesn't just give the price, he explains the why. He uses the historical data of salt belt vehicle degradation to provide context, ensuring the customer doesn't feel exploited. The psychology of the waiting room is a fascinating study in American consumer behavior. In 2026, most shops have moved away from the stale coffee and old magazines model. High-end independent shops now offer co-working spaces with high-speed fiber internet and quiet zones. Why? Because the modern customer's time is their most valuable currency. If a technician like Leo can provide a total diagnostic certainty within 60 minutes, and the shop can provide a space for the customer to remain productive, the friction of vehicle repair is significantly reduced. However, there is a dark side to this digital connectivity: the Google mechanic. Every technician in the US has encountered a customer who has spent 20 minutes on a forum and is convinced they know the solution. Imagine a customer named David who insists his car needs a new alternator because he saw a video online. Leo's testing, however, shows the alternator is fine, but a parasitic draw from an aftermarket remote start system is draining the battery overnight. Sean has to navigate this delicate social interaction. He must validate David's research without compromising Leo's professional diagnosis. This requires a level of emotional intelligence that is rarely discussed in trade schools, but is vital for a successful career. Data from the 2025 to 2026 industry reports suggest that the average American household is keeping their vehicles for a record-breaking 12.5 years. This means technicians are seeing more high-mileage management cases. Leo's documentation must reflect a long-term strategy. He isn't just fixing what is broken today. He is looking at the projected maintenance for the next 12 months. He notes that the timing belt is due in 5,000 miles, and that the tires will likely need replacement before winter. By providing this roadmap, the shop stops being a place of emergency spending and becomes a partner in asset protection. Step by step, the communication loop closes when the repair is finished. Leo performs a quality control check, ensuring no greasy fingerprints were left on the steering wheel, and that all radio presets and seat positions were returned to the customer's preference. He then updates the digital file with the post-repair scan results. This is a crucial data point in 2026. It proves that all computer codes have been cleared, and the vehicle's systems are operating within factory parameters. This report is attached to the final invoice, providing the customer with a digital receipt of the work performed. This synergy between the back-of-house technical mastery and the front-of-house communication is what builds a legacy shop. In an era where corporate chains are consolidating, the independent American technician who can speak the language of both machines and people is becoming a local hero. But what happens when the communication breaks down? What happens when a part fails out of the box, or a repair doesn't solve the issue on the first try? The day is winding down, but the stakes are about to get even higher. As the final customers arrive to pick up their vehicles, we are going to look at the warranty and liability side of the business. You will see how a shop protects itself against part failure, and what happens when a technician has to stand behind their work when things go wrong. We are moving into the world of professional indemnity and the comeback culture. The sun is setting, but the legal and ethical responsibilities of the technician are just beginning to glow. The weight of a technician's signature on a repair order is a legal and ethical contract that carries more gravity than most people realize. In the United States, once a vehicle leaves the bay, the technician and the shop owner are tethered to that machine through a complex web of liability and warranty. Imagine a technician named Sarah, who has just completed a major brake overhaul on a family's primary vehicle. She has replaced the rotors, pads, and flushed the hydraulic system. If she forgot to torque a single lug nut to the manufacturer's specification of 100 foot-pounds, the potential outcome is not just a disgruntled customer. It is a catastrophic mechanical failure on a high-speed interstate. This is why the final minutes of the day are often the most stressful. Every bolt tightened throughout the day must be mentally or physically verified one last time. In the year 2026, the concept of a comeback, where a car returns because the initial repair failed, is the single biggest drain on a shop's profitability and reputation. Historical trends in the automotive industry suggest that a 3% comeback rate is the threshold between a high-performing shop and one that is struggling to stay afloat. For a technician, a comeback is more than just extra work. It is unpaid labor. Under the flat rate system, if Sarah has to redo a job because a part was defective or an installation step was missed, she does not get paid a second time. This creates a high-stakes environment where the pressure to be fast is constantly battling the necessity to be perfect. Let's look at a case study involving a defective out-of-the-box part. Imagine a scenario where Sarah installs a brand new water pump on a customer's SUV. 3 days later, the customer, let's call him James, calls the shop because his engine is overheating. The new pump has a casting flaw that caused it to crack under thermal expansion. From James's perspective, the shop failed. From Sarah's perspective, she did everything right. But she is now responsible for the teardown and replacement of that pump. In 2026, many U.S. shops utilize parts and labor insurance to mitigate these costs. This insurance covers the labor payout to Sarah so she doesn't lose her daily earnings due to a manufacturer's error. But it does not fix the fractured trust with James. Sarah must now perform a forensic analysis of the failed part to prove to the insurance carrier that the failure was mechanical and not due to improper belt tensioning. Step by step, the warranty process in a modern shop is a paper trail of accountability. Sarah must document the failure mode. Was it a seal leak? A bearing noise? An electrical short in a sensor? She uses her digital tablet to upload photos of the defective part alongside the scan tool data, showing the engine temperature logs. This data is transmitted to the parts distributor, who then relays it to the manufacturer in a global feedback loop. This is how the automotive industry identifies pattern failures. If 10,000 technicians across the United States report a similar failure on the same water pump model, the manufacturer may be forced into a technical service bulletin, or even a federal safety recall. Now, imagine the legal landscape of 2026. With the rise of highly autonomous vehicles and ADAS systems, the liability for a technician has shifted from simple mechanical errors to complex software and sensor calibration errors. If Sarah replaces a side view mirror that contains a blind spot monitoring radar, but fails to perform the required aiming procedure, and that vehicle is later involved in a lane change collision, the shop's records will be subpoenaed. In the U.S., right-to-repair laws are constantly evolving, but the burden of proof remains on the service provider to show that the vehicle was returned to OEM specifications. This is why Sarah spends the last hour of her day meticulously filing her post-repair calibrations into a secure cloud-based server. These records are the shop's shield against future litigation. Professional indemnity also extends to the advice given. If a technician tells a customer that their tires have one more season of life left, and a tire blowout occurs a week later, that verbal advice can be scrutinized. Consequently, technicians in 2026 are trained to avoid subjective language. Instead of saying the tires are fine, Sarah records the exact measurement. Tire tread depth is at 4/32 NDS of an inch, which is above the legal limit of 2/32 NDS, but the rubber shows signs of dry rot and age-related cracking. This objective data provides the customer with the information needed to conduct their own due diligence, while protecting the technician's professional standing. Case studies from recent years show a trend toward video walkthroughs as a final step in the warranty process. Sarah might take a quick video of the finished brake job, showing the new hardware and the clean fluid in the reservoir, and send it to James before he arrives. This creates a digital handshake. It shows the customer exactly what they are paying for, and provides a visual record of the vehicle's condition at the moment of delivery. In the competitive American market, this level of transparency is what builds a 5-star reputation on digital platforms, which is the lifeblood of a local business. As the sun begins to set over the shop, Sarah must also manage her core returns. Many automotive components like alternators, starters, and brake calipers have a core value. This is a deposit paid to the manufacturer to ensure the old, rebuildable part is returned. Sarah must drain all fluids from the old water pump, box it up in the original packaging, and tag it with the correct work order number. If she forgets to do this, the shop loses the $50 core credit. Multiply this by 20 parts a week, and a disorganized technician can cost a shop over $50,000 a year in lost credits. This is the inventory management side of being a technician that most people never see. It requires a level of organizational discipline that rivals a warehouse manager. The final task of the day is the tool inventory. Sarah's toolbox is an investment that defines her career. In the United States, most technicians own their own tools, often carrying debt for years to pay for the high-precision equipment required for modern cars. Sarah spends 20 minutes wiping down her torque wrenches and returning her specialized sockets to their shadowed foam inserts. A missing 10mm socket isn't just an inconvenience. It's a potential hazard if it was left inside a customer's engine bay. The FOD, or Foreign Object Debris Protocol, is as relevant in a local repair shop as it is on an aircraft carrier. The shop lights begin to flicker off one by one. The air is still, and the smell of industrial activity is fading. Sarah is exhausted, but her mind is already pivoting to tomorrow. She has a drivability concern coming in at 8 a.m. A vehicle that intermittently dies at stoplights but never leaves a code. This is the white whale of automotive repair. It is the type of problem that can make a technician feel like a genius or a complete failure. In the next part, we are going to dive into the extreme diagnostics of intermittent faults. You will see how we use data loggers that stay in a customer's car for a week to catch a ghost in the machine. We will explore the pin-out testing of main wiring harnesses and what happens when the computer itself has a mental breakdown due to heat-soaked microchips. The day might be ending, but the mystery of the intermittent stall is just beginning to unfold. The challenge of the intermittent fault is the ultimate test of an American technician's patience and diagnostic prowess. Imagine a customer named Chloe who drives a 2023 turbocharged sedan. She describes a terrifying scenario where the engine simply dies while she is sitting at a red light in heavy traffic, but it only happens once every 2 weeks, and the car restarts immediately as if nothing happened. When Chloe brings the car to the shop, the dashboard is clear of any warning lights, and the vehicle performs perfectly during a standard test drive. In the world of automotive repair, this is known as a ghost in the machine. To solve this, a technician like Marcus must move beyond standard mechanical checks and enter the realm of high-frequency data logging and thermal stress testing. In the United States, intermittent stalling is one of the most common reasons for consumer buyback or lemon law claims because they are notoriously difficult for a shop to replicate. Step by step, Marcus begins by connecting a flight recorder to the vehicle's OBD2 port. This is a compact data logging device that stays in Chloe's car for several days. It is programmed to trigger a data capture whenever a specific event occurs, such as a sudden drop in engine RPM or a loss of communication on the CAN bus. Marcus instructs Chloe to press a remote trigger button the moment the stall happens. This allows the tool to save the 30 seconds of data leading up to the stall and the 30 seconds after. This captures the hidden story of the engine sensors at the exact millisecond of failure. While Chloe is out driving with the logger, Marcus analyzes the historical trends of this specific vehicle platform. He looks at case studies in the shop's internal database and national technician forums. He discovers a trend where a specific batch of crankshaft position sensors has been known to suffer from internal thermal expansion. Imagine if a microscopic wire inside the sensor, no thicker than a human hair, expands just enough when the engine reaches a specific operating temperature to lose contact. Once the engine sits for a minute, the wire cools, contracts, and the connection is restored. This is why the car restarts immediately. To test this theory without waiting 2 weeks for a stall, Marcus uses a technique called component stress testing. He uses a specialized heat gun to gently warm the crankshaft position sensor while the engine is idling in the bay. Simultaneously, he monitors the signal on an oscilloscope. A healthy sensor produces a clean, consistent square wave or sine wave pattern. As Marcus applies heat, he watches for the signal to drop or become erratic. This is a high-stakes simulation of real-world driving conditions. If the signal flatlines when the heat is applied, Marcus has found his ghost. This diagnostic certainty prevents the potential outcome of replacing the entire fuel system or the engine control module, saving the customer thousands of dollars and preventing the vehicle from becoming a permanent resident of the service department. However, not all intermittent faults are thermal. Some are related to voltage drops and grounding issues. Imagine a scenario where a loose ground strap hidden behind the engine block vibrates just enough at a specific harmonic frequency, say at 2,000 revolutions per minute, to cause a momentary interruption in the electrical circuit. Marcus uses a tool called a power probe to perform a loaded voltage drop test. He doesn't just check for 12 volts. He applies a dummy load to the circuit to see if the wiring can handle the actual current required to run the components. In the 2026 automotive environment, where vehicles are packed with sensitive microprocessors, a voltage drop of even half a volt can cause a module to crash and reboot, leading to an engine stall or a transmission glitch. Step by step, the hunt continues into the pin-out testing of the main wiring harness. This is a grueling process where Marcus must disconnect the large 80-pin connectors from the engine control module and check the resistance of every individual wire leading to the sensors. He is looking for green crusties, the technician's term for copper corrosion. In states where road salt is used heavily, moisture can actually wick up through the insulation of a wire, traveling several feet inside the harness like a straw. This corrosion increases resistance and creates signal noise that confuses the car's computer. Marcus uses a breakout box, which allows him to probe the circuits while the engine is running without piercing the delicate insulation, which would only lead to more corrosion in the future. Let's look at a case study involving a heat-soaked microchip. In some modern American vehicles, the engine control module is mounted directly on top of the engine to save space and reduce wiring length. Over years of thermal cycling, going from freezing winter temperatures to 200-degree engine heat, the solder joints inside the computer circuit board can develop cold solder joints or microscopic cracks. This is essentially a mental breakdown for the car. The computer might function perfectly for an hour, but once the internal board expands, a processor pin loses contact. Marcus identifies this by using an inverted can of aerosol coolant to spot freeze the module while it's hot. If the car suddenly starts running better when the chip is cooled, the diagnosis is confirmed. The computer itself is the failure point. In 2026, we also have to account for the impact of over-the-air or OTA software updates. Sometimes a vehicle's intermittent stall isn't mechanical or electrical, it's a software bug. Manufacturers frequently push updates to improve fuel economy or emissions. Occasionally, these updates can have unintended consequences under specific high-altitude or high-humidity conditions. Marcus checks the calibration ID of Chloe's car and compares it to the latest release in the manufacturer's Technical Service Bulletin or TSB database. If a software patch exists to address an idle stability concern, the repair might be as simple as a 20-minute reflash of the module. The complexity of these drivability issues is why the United States has seen a shift toward specialized diagnostic technicians who do nothing but hunt these ghosts. These individuals are often the highest paid in the industry, as their skill set bridges the gap between mechanical engineering and computer science. They understand that a lean condition code might be caused by a vacuum leak, but it could also be caused by a faulty mass airflow sensor, a clogged fuel injector, or even an exhaust leak upstream of the oxygen sensor. The ability to look at fuel trim data and determine if the computer is adding fuel to compensate for extra air, or if it's subtracting fuel because of a leaking injector is a master-level skill. As Marcus finalizes his testing on Chloe's car, he has to document his findings with extreme precision. Because the fault was intermittent, he must provide proof of the failure to the warranty company or the customer. He saves the oscilloscope screen captures and the data log showing the thermal failure of the sensor. This documentation is the final step in the masterclass of diagnostics. It provides the customer with the confidence that the root cause has been addressed, rather than just having a part thrown at it. The day is nearly over, but the work of a technician is never truly finished. While Marcus was hunting ghosts, the shop's quick lane was churning through dozens of routine services. In the next part, we are going to look at the volume side of the business. You will see how a shop manages the sheer logistics of moving 60 cars a day through a 12-bay facility. We will explore the pit crew mentality of the modern oil change, the importance of inventory velocity, and what happens when the high-tech diagnostic world crashes into the high-speed reality of a Monday morning rush. The transition from the white whale to the daily grind is about to begin. The Monday morning rush in a high-volume American service center is an exercise in controlled chaos. While Marcus is tucked away in the diagnostic bay chasing electrical ghosts, the rest of the shop is operating under a pit crew mentality. In the United States, the profitability of a repair facility often hinges on inventory velocity, the speed at which vehicles are moved through the system without sacrificing safety or quality. Imagine a lead technician named Carlos who oversees the express service lanes. It is 8:15 a.m., and the driveway is already lined with 15 vehicles. Each driver has a different level of urgency, from the corporate executive with a tight meeting schedule to the rideshare driver, whose income depends on a 30-minute oil change. Step by step, the logistics of this volume are handled by a sophisticated shop management system. As each vehicle crosses the threshold, a digital geofence recognizes the car's VIN via an onboard transponder or a high-speed camera system that scans the license plate. This immediately pulls up the vehicle's entire service history on Carlos's tablet. He can see that a customer named Sarah has missed her last 2 cabin air filter replacements and is due for a brake fluid exchange based on her mileage. This data-driven approach allows Carlos to prepare the necessary parts before the car even touches a lift. In 2026, the potential outcomes of a disorganized morning are lost revenue and a backup that can paralyze the shop for the entire week. Let's look at a case study of the modern oil change, which is no longer a simple drain and fill operation. Carlos manages a team of 2 lower-level technicians per bay. While one technician is underneath the vehicle using a pneumatic oil extraction system, which pulls the old oil out through the dipstick tube to avoid stripping the drain plug, the second technician is performing a digital battery health test. They are using a conductance tester that sends a specific frequency through the battery plates to measure internal resistance. If the resistance is high, even if the car starts fine today, the data suggests a potential outcome of failure during the first cold snap of winter. Carlos captures a screenshot of this state of health graph and pushes it to the customer's phone in real time. Inventory velocity also applies to the parts department. In a high-volume shop, the parts runner is the unsung hero. Imagine if a technician finds a seized brake caliper on a vehicle that was only supposed to be in for a tire rotation. If the shop has to wait 2 hours for a delivery from a local warehouse, that lift is dead space. To combat this, modern U.S. shops use just-in-time inventory algorithms. By analyzing historical trends of the most common failure points for the top 20 vehicle models in their specific zip code, the shop keeps high-velocity parts, like specific brake rotors for a Ford F-150 or ignition coils for a Honda Civic, on the shelf at all times. This allows for a same-day turnaround on complex repairs that would have previously taken 48 hours. The pressure of volume can lead to human error, which is why standard operating procedures, or SOPs, are the religion of the shop. Every technician follows a double-check protocol. For example, when rotating tires, the primary technician uses a torque stick on an impact wrench to get the lug nuts close to the specification. A second technician must then follow behind with a manual, calibrated torque wrench and click every single nut in a star pattern, marking each one with a dab of erasable paint. This visual confirmation is a safety safeguard that prevents wheels from coming loose, a scenario that, while rare, remains a high liability risk in the industry. Imagine the scenario of a comeback in a high-volume environment. If a car returns with a leak because an O-ring was pinched during a hurried fuel filter replacement, it doesn't just cost the shop the labor to fix it. It disrupts the entire flow of the Monday morning rush. Carlos has to pull a technician off a paying job to address the warranty issue. This is why quality at the source is emphasized. Historical trends show that shops that prioritize speed over precision eventually suffer from a revolving door of both customers and staff. In 2026, a technician's fixed right first-time score is a primary metric for their performance reviews and compensation. The daily grind also involves the management of the shop's physical infrastructure. With 12 bays running at full capacity, the wear and tear on equipment is immense. Carlos starts his day with a lift safety inspection. He checks the hydraulic fluid levels, looks for fraying on the steel cables, and ensures the mechanical locks are engaging properly. A failing lift is a life-threatening hazard. In the U.S., OSHA, the Occupational Safety and Health Administration, sets strict guidelines for these inspections. A technician's day involves a constant awareness of their surroundings. The sound of a compressor cycling too frequently might indicate a leak in the shop's air lines, which wastes electricity and reduces the power of pneumatic tools. Let's discuss the multi-brand reality of the modern independent shop. Unlike a dealership that only sees one make of car, Carlos's team might work on a Tesla, a Chevrolet, and a BMW in 3 consecutive bays. This requires a massive investment in service information subscriptions. Each manufacturer has its own proprietary repair procedures. For instance, the reset procedure for a maintenance light on a Toyota is vastly different from the service mode sequence on a Land Rover. Carlos's team uses a centralized knowledge base that aggregates these procedures, allowing a technician to switch mindsets in seconds. This mental agility is the hallmark of a professional in the 2026 automotive landscape. By mid-morning, the quick lane has processed 20 cars, and the shop is humming with the sound of air tools and cooling fans. But there is a hidden element to this volume: the digital paper trail. Every gallon of oil, every crush washer, and every ounce of refrigerant must be tracked for environmental and financial reasons. In the US, the billable hour is only part of the equation. The parts margin and supplies recovery are what keep the lights on. Carlos ensures that shop supplies, the aerosols, lubricants, and cleaners used in every job, are billed correctly through an automated dispensing system that requires a technician to scan the work order before the cabinet opens. As the morning rush begins to taper off around 11:30 a.m., the focus shifts from volume back to heavy repair. The cars that were dropped off for deep dive diagnostics are now being torn down. The transition is seamless but requires a change in tempo. The frantic energy of the express lane gives way to the surgical precision of the engine bay. Carlos moves from bay to bay, acting as a mentor to the junior technicians, showing them how to identify a tensioner pulley that is just beginning to chirp or how to spot a micro-leak in an AC condenser using ultraviolet dye. The day is a marathon of technical challenges and logistical puzzles. We have seen the high-stakes diagnostics and the high-volume grind, but what about the person behind the wrench? What is the actual career path for a technician in 2026? How do you go from an apprentice to a shop owner? And what are the financial realities of this trade in a world of increasing automation? In the final part of this masterclass, we are going to look at the future of the technician. We will explore the earning potential across different regions of the United States, the impact of artificial intelligence on repair times, and the human factor that ensures this trade will never be fully replaced by robots. The sun is reaching its peak, and we are about to reveal the roadmap for the next generation of American automotive masters. The ultimate conclusion to a day in the life is coming up next. As the midday sun hits its zenith over the repair shop, we move into the final and most significant chapter of this masterclass: the evolution of the American technician. In 2026, the image of the grease monkey has been entirely replaced by the reality of the diagnostic engineer. Imagine a young technician named Ethan. He started as a lube tech 3 years ago, and today he is navigating the complex path toward becoming a master ASE certified technician. In the United States, this career trajectory is no longer just about learning how to turn a wrench. It is about managing a personal business within a larger infrastructure. The financial reality for a technician in 2026 is a blend of specialized skill, heavy tool investment, and a commitment to lifelong learning that rivals the medical profession. Step by step, the roadmap for a next-generation master begins with certification. The National Institute for Automotive Service Excellence, or ASE, remains the gold standard. To reach the top tier, Ethan must pass a battery of 8 core exams covering everything from engine repair and automatic transmissions to electrical systems and advanced engine performance. Historical trends in the U.S. labor market show that certified technicians earn significantly higher wages than their uncertified peers, often seeing a 20 to 30% increase in their base hourly rate. But the certification is just the entry fee. The real work happens in the bay every day, where the flat-rate pay system dictates that Ethan's speed and accuracy are the primary drivers of his take-home pay. Let's look at a case study of the modern technician's tool debt. Unlike almost any other profession in the United States, automotive technicians are expected to provide their own equipment. Imagine if a surgeon had to buy their own operating table and scalpels. For Ethan, his tool chest is a rolling monument to his career. He has invested over $40,000 in high-precision torque wrenches, digital multimeters, thermal imaging cameras, and specialized pullers. In 2026, many technicians use tool credit programs through major distributors like Snap-on or Matco. While this allows them to access the technology they need to do the job, it also creates a unique financial pressure. The potential outcome of a successful career is a debt-free 6-figure income. But the early years are a gauntlet of high expenses and low initial returns. This is the hustle of the American trades that is rarely discussed in high school career centers. The impact of artificial intelligence in 2026 cannot be overstated. We are now seeing AI-assisted diagnostics integrated directly into the shop management software. When Ethan scans a car, the AI compares the live data stream against millions of similar case studies across North America. It might suggest, based on a 98% probability, that a specific short-to-ground in the wiring harness is located behind the left rear wheel well. This doesn't replace Ethan. It makes him more efficient. The human factor remains irreplaceable because the AI cannot feel the play in a steering rack or smell the burnt sweetness of a slow coolant leak. The technician of 2026 is a hybrid, part data analyst and part mechanical surgeon. Imagine if Ethan decided to specialize in the EV revolution. In 2026, the demand for high-voltage technicians has outpaced the supply by a ratio of 10 to 1. This specialization requires a completely different set of safety protocols and tools. Ethan must be certified in global EV standards, learning how to safely discharge a 400-volt battery pack, and how to diagnose internal resistance issues within individual battery cells. Historical trends suggest that as the U.S. fleet continues to electrify, the technicians who bridge the gap between internal combustion and electric drive units will be the most recession-proof workers in the country. They are the ones who keep the wheels of American commerce turning. Whether those wheels are powered by gasoline or lithium-ion, the human factor also extends to the mentorship model. In every American shop, there is a graybeard, a veteran technician who has seen every mechanical failure imaginable since the 1980s. In our scenario, this is Frank. Frank doesn't use the AI as much as Ethan, but he can tell you a car has a misfire just by the way the exhaust pulses against his hand. The transfer of knowledge from Frank to Ethan is the heartbeat of the industry. This apprenticeship culture ensures that even as the technology moves at light speed, the fundamental principles of physics and mechanics are preserved. It is a brotherhood and sisterhood of the belt and pulley, a community that speaks a language of torque, tension, and tolerance. As we look at the broader economy, the automotive technician is a vital pillar of the United States infrastructure. Without them, the logistics chains that deliver our food and the emergency services that protect our homes would grind to a halt. The earning potential in 2026 for a top-tier technician in high cost-of-living areas like the Northeast or the West Coast can exceed $150,000 annually. However, this comes at the cost of physical wear on the body and the mental stress of being responsible for the safety of thousands of families. It is a career of high stakes and high rewards, suited for those who find satisfaction in the click of a perfectly torqued bolt and the purr of a rescued engine. Step by step, the day ends as Ethan rolls his tool chest shut and locks the heavy drawers. He wipes the sweat from his brow and looks at the row of vehicles he has touched today. Each one represents a problem solved, a disaster averted, and a customer who can now get to work tomorrow. The day in the life of a technician is a cycle of frustration and triumph. It is the grit of the American worker meeting the polish of modern technology. As the shop doors finally slide down and the security system arms, the silence of the garage is a testament to the thousands of moving parts that are now, thanks to Ethan, moving in perfect harmony. The sun has set, but the story of the automotive industry is only beginning its next iteration. We have covered the diagnostics, the heavy repairs, the digital calibrations, and the environmental stewardship. But there is one final frontier we haven't touched: the right to repair movement and the legal battle for the soul of the car. In our upcoming deep dive, we are going to explore why some manufacturers are trying to lock technicians out of their own cars, and how the grassroots movement of American mechanics is fighting back in the halls of Congress. What happens when a car becomes a black box that only the manufacturer can open? Is the era of the independent shop coming to an end? Or is a new golden age of DIY and independent repair just around the corner? The battle for the future of your vehicle starts now. We have shown you how the car is fixed. Next, we will show you who truly owns the data inside it. Stay tuned for the ultimate investigation into the politics of the pavement.